Hello everyone, this video covers section 5.5, which is error controlling. And as the name suggests, the idea is how to control the error of the different methods. Now in section 4.6, I believe, so section 4.6, we already saw adaptive methods. And remember, the idea at that time is having the same value for each all the time or the same step size may not give you the best approximation, especially when the function look something like this. Okay, so this is from chapter 4. And remember, for when we cover adaptive methods at that time, the idea is that you have to choose a different value of h at every step to increase the accuracy. So the idea is going to be very similar here, which it should be not surprising because there is a connection between differential equations and integrals. Remember, these adaptive methods were for integrals, and to solve a differential equation, in essence, you have to integrate. In this section, adapted means the following. We're going to adapt the number and position of the nodes used in the approximation to ensure that the truncation error is kept within a specified bound. In essence, what this means is that the step size could be different every step. It doesn't have to be the same step size throughout the whole process. Now consider the one-step method to solve the same differential equations with the solving all alone. Notice here the difference is that h now has its own subscript, which it didn't have before. And this is the local truncation error. So therefore, the ideal difference equation method, which will look like this, has to have the following properties. So that is the ideal difference equation method should have the property that given a tolerance, let's call it epsilon, which obviously has to be bigger than 0, and a minimal number of mesh points or steps, that this ensures the global error YTI minus WI is less than epsilon for I equals to 0, 1, all the way to. Well, remember, this is called the global error. Now, in general, we cannot really compute the global error, but there is a connection between the global error and the truncation error, which we are able to compute to the truncation error or local truncation error that we're able to compute. And that's where we're going to go next. Also note that if you want to control the global error and also have a minimum number of steps, that's impossible to achieve if you have a fixed value of h. Consider the next two approximations we have. This is approximation number 1, and this is approximation number 2. Notice that the first one is order of h to the n, and this one is 1 degree higher. This one is hn plus 1. And these methods are generally found by doing a Runge-kutta modification of the Taylor method. So that's how we usually will get these two. Notice that we also have h in here, which means that h is also a variable, so it's not a constant step size anymore. So you have it here, and we have it here. Next, we need the following assumption. Suppose that wi is approximately equals to y of ti approximately equals to wi tilde. And as before, we'll start with a fixed step size h to approximate or to create approximations to yti, which the first one is wit1 and the second one is witi tilde. Recall that the formula for tau I plus 1 was equals to y of ti plus 1 minus y of ti divided by h minus phi of ti y of ti h for some function phi. This should have a h in here. Then based on this assumption right here, then this should be y of ti plus 1 minus wi over h minus phi of ti wi h, which if we use the one of the best math tricks to multiply by 1, remember you do that, it doesn't change the equation, then now you can factor the 1 over h and we get the following. This will be now y of ti plus 1 minus wi plus h phi of ti wi h, everything divided by h, and there is a bracket here. Here this h is just this h right here, and you can combine these two in the bottom, so that's how we get this one. However, remember by definition, all of this is equals to wi plus 1. So therefore from here we get wti plus 1 minus wi plus 1 over h, where this is just equals to this blue part. Notice that this result by itself is not very promising because this is what you're trying to approximate, so therefore this doesn't give you much information for now. Now if we do the same thing for the tilde part, so then similarly we have the tau tilde of I plus 1 of h is going to give us 1 over h y of ti plus 1 minus wi plus 1 tilde. Alright, so then notice the following. We have the ti plus 1 of h as equals to 1 over h y of ti plus 1 minus wi plus 1. So that's what we have so far. Then, and if we add and subtract 0 to this, which again is one of the most common tricks in math, so therefore if we do plus omega tilde I plus 1 minus omega I plus 1 tilde, and simplify, from here we end up with the following. This is 1 over h. This will be y of ti plus 1 minus wi plus 1 tilde plus 1 over h. Then this will be wi plus 1 tilde minus wi plus 1. How do we get that? This is just basic algebra, but just to be sure. So if you combine this with this, it gives you that. And then if you combine this with this, it will give you this part. Now remember that by definition, all of this part is equals to tau tilde I plus 1 of h, and then we have the extra part in here, which is w tilde I plus 1 minus wi plus 1. Okay, so this was the green part. This. Now, one thing that is very, very important to remember is that you recall from a few minutes ago, this is order h to the n. Well, this one is order h to the n plus 1. So therefore, that means that this equation, or this side, has to match this part. So that means that this is not very important. So this is not very important. Okay. And therefore, we only have to focus on this part. So we have to focus on this one. All right, let me fix this part. This should be focus. This should be n to the 4, h to the n. This should be focus. So this is the part we had to focus on. So therefore, this implies that tau I plus 1 of h is approximately equals to 1 over h times wi plus 1 tilde minus wi plus 1. And this is easy to compute. It doesn't mean it's fast, but it's easy to compute. So this is it. This is an easy way to compute. So easy to compute an approximation to the local truncation error of OH to the N. All right, so we just got the following result. The local truncation error can be approximated as 1 over h wi plus 1 tilde minus wi plus 1. If we take the absolute value of this, we're going to call it r. So r is going to be 1 over h, the absolute value, wi plus 1 tilde minus wi plus 1. So r is just the absolute value of this part. And here, this is h. All right, so now the goal in here is the following. The goal is to adjust the step size h to keep it within, and to keep it means to keep the method within specify bound, which usually is epsilon, or a specify bound or tolerance. Okay, now since we already agreed tau of I plus 1 of h is order of h to the n, then it is a reasonable assumption to assume that tau I plus 1 should be approximately equals to a constant times h to the power of n. So that's a reasonable assumption. All right, we're going to introduce a new variable, the variable q, which is the one we're going to use to keep track of the step size, and it's going to help us to change the step size at every step. So if this is a k, that means the tau I plus 1, say of q h, this will be k q to the n h to the n, which is equals to q to the n times k h to the n. But remember, this is what we define to be tau, so therefore this should be equals to, or approximately equals to, q to the n times tau I plus 1 of h, which is approximately equals to q to the n over h times w I plus 1 tilde minus w I plus 1. Okay, remember the tau of I plus 1 from here is equals to this part. Therefore, if we want tau I plus 1 of QH, say, to be bounded by epsilon, then this implies the Q to the N over H times the absolute value of WI plus 1 tilde minus WI plus 1 should be less than or equals to epsilon. Now it will solve for Q, and everybody should check this. This is basic algebra. You end up with the following. This will be epsilon H over the absolute value of WI plus 1. WI plus 1. Remember that the first one is tilde. Everything to the 1 plus m power. 1 over m power. And this could be written, it's not really necessary as this, where we already define R before to be the absolute value of this over H. So therefore this is going to be the bound or rule we're going to use to choose the value of H at each step. All right, on the next page, we're going to look to a specific example of this. Remember, they need to have two methods, one of order n and the other one of order n plus 1 in order for this to work. All right, let's look to the Runge-kutta failure method. This is one of the most popular error controlling techniques. Okay. Here, the first method is order h to the phi, or the second one is order h to the 4, and this uses Runge-kutta methods, obviously. The first one is a Runge-kutta of order 5, and the second one is a Runge-kutta of order 4. As you can see, this is very, very messy, and it takes a long time to compute by hand, so that's why you want to do a program to compute this, because it will take a long time to do by hand. Here, K1 is equals to H f of Ti Wi. K2 is equals to H f of Ti plus H over 4 Wi plus 1 over 4 K1 and so 4 K3 is equals to this Wi plus 3 over 32 K1 plus 9 over 32 K2 and so 4. So the last beauty equals to H f of Ti plus H over 2 Wi minus A over 27 K1 plus 2 K2 minus 3,544 over 2565 K3 plus 1859 for 1 over 4 K4 and then minus 11 over 40 K5. So as you can see, this could be a nightmare to do by hand, but everybody should try this at least for one step. Notice how this method only requires the evaluation of f 6 times for each step, while if you were using the regular Runge-kutta of order 4, it requires at least 4, and if you do the Runge-kutta of order 5, it will require at least 5 to 6 evaluations. So at minimum, to compute both of them, it will require at least 10 steps. 10 evaluations of f per step. So therefore, this method, the Filbert Runge-kutta method, so this one is at least 40% more efficient than using just Runge-kutta by itself. Remember that Q was supposed to be less than or equals to epsilon h over the absolute value Wi plus 1 tilde minus Wi plus 1, everything to the 1 over n powered. So now once you compute this value at every step, you're gonna decide if the value for h is good. If not, you had to modify it, and this is technically going to be the rule. So when k, if you compute the value for q, if you compute the value for q and q is less than 1, then you're going to reject the initial choice for h, and add the I step and repeat the calculation now using the new step size that is going to be q, whatever q you got, times h. So this is going to be the new step size. Notice that this has the potential to therefore double the amount of work compared to methods that do not use the error control. Now, when Q is greater, when Q is greater or equals to 1, then we accept the computed value, at the or of the I step using the step size h, but we change, so we need to change the step size to still Q over H to use on the I plus 1 step. Now let's do an example. So let's say we use the previous method where the tolerance is equals to 10 to the negative 5. So this should be 10 to the negative 5. Remember, this is epsilon. And we want to have a maximum step size of 0.25. So H max is going to be 0.25. The minimum is going to be 0.01. Here we have T0 is equals to 0 and W0 is equals to 0.5. For this method, we use the slightly modified version of Q, and the reason is that remember that if this gives you the wrong value, or if this is less than 1, you have to repeat the steps, and that's not a desirable quality. So therefore, you want to be conservative on picking the choice of Q. So for this particular method, this is usually the value for Q. And how do we get to this point? Well, remember that we're using a Runge-kutta order 4, so n is equals to 4 in here. So therefore, this actually comes from epsilon h over 2. So this is the part that is used to modify the method. Wi plus 1 tilde minus Wi plus 1. Everything to the 1/4 power. And if you simplify this, if you do the 4 power of 1/2, is actually equals to 0.84, so you should check that. But the point is that for this method, this is the value for Q that we'll be using. Now, as I say before, to compute this by hand, this is very, very painful. Everybody should do this at least once, the whole thing, but here are the results. So here K1 is equals to 0.375, so this is actually the easiest one to find. Then K2 is equals to 0.3974609. K3 is equals to 0.4095383. K4 is equals to 0.4584971. K5 equals to 0.4658452. And then finally K6 is equals to 0.4204789. Now, once you plug these numbers back in the beautiful formula we have before, we end up with W1 tilde is equals to 0.9204A70, and W1 is equals to 0.9204AA6. Recall that the value for R was equals to 1 over H. This is Wi plus 1 tilde. This is absolute value, actually minus Wi plus 1. So therefore, if we plug in the values for Q, we end that Q is equals to 0.84 times, this should be 0.00001, everything to the 1, 4. And on the bottom, this is equals to 0.00064. And this is around 0.93914, which is clearly less than 1. So therefore, for the next step, so the new step size is going to be equals to H new, maybe 0.93194 times H, which was 0.25, which is equals to 0.234787. And since this value for H, the original one, which was 0.025, was rejected, now you have to start the process again and go through all of this beautiful thing using this new value for H, which again, it can take a while, but if you are bored and you have nothing else to do, you should try to do this by hand again, the whole thing. All right, so that's it for this section.